This is demonstrating the surgical technique for the Enforce. We're going to start instrument-wise review. These are the Enforce screws. They are cannulated fully and partially cannulated designs. They attach this disposable sheath to the head through an external thread mechanism that allows for insertion of materials and also for insertion of the screw. Basic instruments in the set consist of a K-wire and drill guide, the 1.4 millimeter K-wire, the depth measurement over the K-wire, a cannulated 2-7 drill, a cannulated hex driver, and a solid hex driver with standard AO attachment small fragment type screwdriver handle. So now we're going to start the procedure. We're going to take this multi-hole cluster. We're going to do the first hole first. We're going to start with a K-wire. So we'll load this up on a wire driver. We'll have made a skin incision, or if it's an open procedure, you'll put the drill guide up against the bone. The length of the K-wire drill sleeve minimizes deformation of the wire. You're going to go down a minimum of 5 to 10 millimeters below the articular surface. And this would be typically performed with fluoroscopic C-arm guidance. You'll move the insert. We'll take a depth measurement, read off the length of the desired screw, and then we're going to drill the proximal cortex with the 2-7 drill. This really depends somewhat on the quality of the bone. Pull out the wire, and in this scenario I'm using a partially cannulated screw. So I'll remove the K-wire. If you look in the ends of the screws, there's a fully threaded design and a fully threaded partially cannulated design. So this is closed in, this is fully cannulated. The reason to use the closed design is if there's a chance that the screw may have bicortical fixation and you wouldn't want any biomaterial delivered to the outside tissues. We'll now attach the sheath for the injection port to the Enforce screw through the external mechanism. These screw lengths come from 25 to 75 millimeters in 5 millimeter increments. And the unique spiral pattern is the actual vent system and depressurization system that allows the introduction of materials over length. Currently, the FDA has only cleared the ETEX Beta BSM and ETEX Keragen as compatible bone void fillers because of their biological compatibility. We'll now take the cannulated screwdriver, insert it in through the sheath mechanism, and then we can either insert it by hand or power. We'll insert this one by hand. It threads as a self-tapping screw, pretty much like a regular 4-0 fully threaded cancella screw. The depth is carried down until the plastic sheath is flush with bone. This may be placed as a headed design or a headless design depending on the depth of insertion. So now that the sheath is down firmly, I'll remove the screwdriver and we'll mix the cement. Okay. This is the ETEX Beta BSM. The Beta BSM is superior for the use of bone voids as occurs with fractures or neoplastic lesions or cysts. This is a 5 cc batch of material. Our estimated defect is approximately 5 cc's. There is minimal waste with this system because the bone void filler is contained within the sheath and screw and delivers it inside the bone rather than have the material disperse outside in the soft tissues during insertion. The 3 cc's of saline is added to the nanocrystalline Beta BSM mix. Once hydration begins, you let the syringe rest for 30 seconds. This is an isothermic cement, so it actually requires the elevation of the temperature to 37 degrees centigrade. When you're operating on an extremity, typically the extremity is close to the room temperature. So you have plenty of working time. You want to keep the material within the tube so it doesn't change its hydration ratio. The hydration ratio is really what governs the aggregation process of the cement. After approximately 30 seconds of rest, then usually it's 12 to 15 pushes is sufficient to mix the cement. We'll go ahead and start mixing now. And it's just a gentle hand pressure. This gets the extra air out of the system. Now we'll transfer the material into the small syringe. Okay. Couple the cement. And now we'll start injection. It takes approximately 1 cc to fill up the inside of the screw and the sheath. You can see the material flowing into the defect and actually getting a nice seal and pressurization. Okay. That's sufficient fill for this one. So we'll now remove. So we've actually saved some material. Because this is still an isothermic cement, we can contain this and use it for another hole by placing it back in the sheath. We'll now go ahead and do the final seating. We'll change out the cannulated screwdriver for the solid screwdriver. Insert it through the sheath, which gives us the extra bulge or flush of cement. We'll now loosen. And then we'll sink the head in place for final compression of the fracture. And this gives us a headless type construct that's flush to the bone. The design of the screw permits extraction of the screw after the cement hardens with an approximately 1 to 2 Newton meters of force. So that's digital extraction. All right, so if you set that aside to hydrate, and then we'll take the K-wire and the drill sheath again. This is best done with image intensification and fluoroscopic control. I'll insert the K-wire. We'll now take our depth measurement again. Okay, 50. And so now I'm going to go ahead and insert the cannulated screwdriver. Reassemble the cannulated screw this time to show going over the wire. And I'm going to drill the hole. So now we'll assemble the cannulated screwdriver. And for the longer screws, I recommend insertion under power. This is a 50 millimeter length, fully cannulated in-force screw. So now we're going to remove the wire. And we'll take the cement, proceed with mixing. Let me bend it a little bit. We'll load the injection small syringe. We'll start slow injection. We'll fill the first hole first.